So, hello everyone. This is the second incarnation of Shannon Channel Talks. Basically, these are going to be talks on coding theory and information theory broadly. In this second incarnation or second episode, our presenter is Yonatan Kaspi from UCSD. He did his PhD at Technion, and he is going to talk on searching with measurement noise. And we are joined by IIT Salim El-Ruayev's group from Illinois Institute of Technology and myself from UCSD. So I'll hand over the mic to Jonathan.
Okay. So does this work? Can you hear me?
Yes, we can.
Okay, great. Okay, then we can start. Okay, so the title is Searching with Measurement-Dependent Noise. This is joint work with Ofer Shayevitz from Tel Aviv University and Tara Javidi from UCSD. And I start with standard outline of motivation. I'll have the motivation for this problem and sample some previous work. And then we'll start by searching for one target. We have two kinds of scheme. One will be adaptive and the other non-adaptive. And then in the last 10 minutes, more or less, we'll let the single target spawn into multiple targets. And then again, we have the same problem of locating all of them. And then we'll wrap up. Okay, so let's start by motivation. So assume we have a target somewhere on the, say, some interval, say the unit interval, and we want to locate it. Only the target is placed in a noisy environment, meaning there are many other items in this environment which might look as our target. So there are many ways to try to search. For example, we can define a very small window and just linearly go from, say, left to right, trying to locate the target. So if the window we look at is very small, we'll get a small amount of noise, but it will take us forever to search. On the other hand, we can search bigger areas, like in binary search, we would look for half of the region or any other subsets of interval on this region, but then we'll get a lot of noise in our samples. So as a concrete example, let's look at searching with satellite imagery. Okay, so let's say we assume we look for a target in a vast area, say the sea, somewhere in the sea. And I started by give you an image of a large area of the sea, a large chunk, let's say, I don't know, a kilometer by kilometer of sea. And then I ask you, do you see the object we're looking for? And I ask you just yes or no. And then you see this image has a lot of noise in it. It has clouds and waves and whatever. And then, depending on your answer, or maybe independent on your answer, I will give you another image, same resolution, so same quality of image, just zoomed in into a much smaller region. And then I ask again, do you see the object, yes or no? And the point I'm making here is this image. Do you see my pointer? This image is much clearer, right? You get the answer you give me will have much less noise than this image here. Okay, so this is the basic idea. And in fact, both in both cases, your answers might be wrong, meaning they are noisy. So these images come from the search for the plane which was lost, the Malaysian plane which was lost a year ago. And they have this exact problem of zooming in or not. And this phenomenon of measurement-dependent noise, where the noise depends on how you measure your environment, I mean, we see it in these satellite images, but they're not. You have any system which we can trade off sensitivity with quality will have this. For example, the microphone sensitivity, the ISO setting in your camera, and so forth. So a bit more concretely, we have a target placed on the unit interval. Okay, so we denote it by this red X here. We want to locate it with some resolution we call delta. And the way we search for it is the following. At each stage, at each time unit, we give our system a query region, these gray areas, which can be anything. So it can be a contiguous interval, like from 0 to half, as you would do in binary search. or it can be any other subset, like union of intervals. And what I get in response is a binary output, which indicates if I hit the target or not. So in this case, I missed. So the indicator will be 0 plus noise. And it's measurement dependent noise because the probability that this noise flips my indicator bit, depends on the size of the Fourier region. Okay, and we'll get more concrete mathematical model in a few slides. So if you would force ourselves at this point to look at it as a channel coding problem, we can think of these regions as an input to the channel, these gray regions. We can think of this binary output as the output of the channel, the noisy output of the channel. And in this case, there is only one controller which sees both. It both sees the input and the output, and this means in a channel coding perspective, we have clean feedback. We see both input and output to the channel, and we'll use it a lot in the following slide. Only this, just here, I will say that in this problem, clean feedback actually makes sense. Unlike many communication problems where you assume you have a noisy channel going forward and then somehow you get a clean channel going backward. But in this problem, it actually makes some sense. So just a sample of related previous works. So we're not the first to consider search problems in the information theory literature. The first were Bernashev and Zigandierov, and they had a model in which they also have a target placed on the interval, and they give their system a location on the interval, and the answer they get is the target to the right and or to the left, and this answer they get might be flipped with some fixed probability, which we call P. And they show that the rate of the search, which we'll define in a few slides, is related to the capacity of a binary symmetric channel with flip probability P. And the way they showed this is they used the Horstein adaptive scheme for coding with feedback over a binary symmetric channel. So they used an adaptive search, and then we'll see in a few slides that there is no need for adaptive search in this case, and they could have done it with non-adaptive search. Another line of works which is very related to our problem, at least to the many target problem, is works on group testing. A group testing problem is a problem in which you have a population of, say, n people, and k of them are, say, sick with something, and you want to find the k people with while minimizing the number of, say, lab tests you're doing. So you take some samples, say, blood samples from all your population, and then again, you can go linearly, just every sample sent to the lab and see if the person is sick or not, or you can mix groups of tests together and then test all of them in just one lab test. So this problem is very related to our problem. There's a huge body of work on this problem, but mostly on the combinatorial work, meaning there is no knowledge. The lab tests are whatever you get as answer is the right answer. There's much less work on noisy group testing, and then and most of these works on noisy group testing only give order results, meaning that they give bounds on the number of samples you need as an order of the population size and the number of targets. And as information theorists, we usually care about the concept. For example, if we know that the Go code achieves capacity or half capacity, which is the same order, we still care about them. The Go code that achieves capacity is much better in our viewing, although both of you achieve the same order result, the same order of rate. So an exception to the works which give order results is the work of Atiyah in Saligrama, the recent work, and they did with noisy group testing, and I will mention their work later. But they assume the fixed noise model, in some sense at least, like Bernashev and Zingler. The lab results might be wrong with some fixed probability. Okay, another line of works which we'll need here is the works on error exponents. So when doing channel coding, we're coding over a channel. With feedback, Bernashev in 76 showed that the reliability function, when you do variable rate coding, is given by this expression here, which is basically so C1 and C are functions of the channel itself. C is capacity. And this means that the error exponents, once you have feedback and you're doing variable rate coding, is a linear function going down from C1 all the way to 0 when the rate reaches capacity. And we'll see it in a second. So if I just draw for example, for the binary symmetric channel, if I draw the random, the exponents, the known exponents, so without feedback, the exponent is not known. We have an upper bound and lower bound. So the lower bound is the random coding bound. The upper bound is the sphere packing bound. So these are the blue and green lines here. And with feedback, what Bernashev showed is that you can get actually this red line. So all of them meet 0 at the same point of capacity. But feedback increases the reliability, the error exponent, by a lot, as we see here in a specific example of the binary symmetric channel. And in 79, Yamamoto and Ito gave a very simple...
W? Can you hear us?
Yeah.
What is W? What is W?
What is?
What is the y-axis here?
The actual value of the exponent.
Oh. So the capacity is the same, but the exponent is...
Yeah, capacity is here, right? Capacity is where all these lines meet 0. The exponent is 0 once you reach capacity, right? But, I mean, the value, the actual exponent you get is much, much higher with feedback.
Is there a scheme?
Yeah, so yeah, it's a good question. So Yamamoto and Ito in 79, at this point here, they gave a very simple scheme to achieve it. Bernashev also gave a scheme, but it's not that simple. So the Yamamoto and Ito scheme basically use your regular code for the first phase. Just send your message using without harnessing feedback. And then using feedback, the encoder and decoder, the encoder know the decision of the decoder is going to make.
Okay.
And then all it needs to do is signal if the decoder if it's right or wrong. Right. For example, so over a binary channel, say the encoder will send, say, a sequence of 1s if the decoder is right, or a sequence of 0 if the decoder is wrong. And then the decoder is basically faced with a hypothesis, binary hypothesis. Is checking if it was right or wrong, and this is why you get this huge increase in reliability. Yeah, so and if the text is wrong, just everything starts over again. We just restart.
Even if there's one error, you restart the whole thing.
So if the decoder detects that he got an error in the first phase, we start everything again. But the thing is here is this: as long as this is happening with a small probability, it doesn't increase your average rate. Okay, so rate is not changed, but the exponent goes up. Okay, so this is, and we'll have a scheme like this in our search problem. Okay, so let's focus on the single target search, and we need some notation. So in this presentation, W will denote the location of the target on the unit interval. So the location of this red X here. And we assume nothing on W, so there's no distribution on it, just a number. Sn will denote the quarried region at time n, so the gray areas we use to query where the target is at time n. The output will be denoted by Y, and Y is composed of two elements. The first is X, which is just the indicator, did we hit or miss the target with our search region. Right, so in this case, X is 0, plus noise, denoted by Z, and Z is Bernoulli, where the probability that Z is 1 depends on the size of the quarry region. Okay, so this small p here now is a function of the size of the cardinality of the quarry region, and it's basically a function from 0 to half into 0 half. And all we want it to be is non-decreasing. So if you query a larger region, it will give you more noise. So for example, if this function is just constant, then we are back in the standard noise model, which is just you flip the answer with some constant probability. Okay, and it can depend in any way on the for example, p can be a linear function. like here. And in all the numerical examples I show, I will assume that the amount of noise you get is a linear function of the size of the core region. Okay, and tau will denote the number of queries we're making until we make a decision. Yeah, until the decoder says where he thinks the target is. Okay, so under this notation, a strategy is just a choice of these regions, the SNs, when to make a decision, and then what decision to make, so the estimated location of the target. And we can think of two kinds of strategies. The first is non-adaptive. Non-adaptive meaning that all these SN, all the regions are fixed in advance. And I just run my queries, see all the outputs, and make a decision. So in this case, tau is just a constant. We call it n. This is very similar to channel coding, just a block, doing block code. We have our code. It's fixed. We send the row in the code book, say length n, and then the decoder makes a decision. So this is non-adaptive scheme. On the other hand, we have feedback here, as I said a few slides ago, and then we can do adaptive scheme. So in an adaptive scheme, SN will generally depend on the past answers we get. So a famous example of adaptive search scheme is binary search. Right, like divide and conquer by binary search, where you start with looking at half the region, and then if you see the target, you zoom in into this half. If not, you zoom into the other half, and then so forth. This is an example of adaptive scheme, and we'll see our adaptive scheme here. Of course, binary search will fail in a noisy model.
I have two questions.
Yeah.
So for the noise model, so does it make sense to consider, first is P a function of Sn, right? The size of Sn. Is it always between 0 and 1?
So, I mean, you'll need to scale it if your interval is 0, right? But basically, it's 0 half, because at least with one target, it doesn't matter if,
And also, does it make sense to think of it as, to consider a Gaussian noise? Because if you think you're dividing this segment into small pieces, and then all the noises add up.
Yeah. It's not the model we have here, but of course, it does make sense. So this is a simplified model in some sense.
The other thing is
setting, you can choose the variance to depend on the. Right? Yeah, sure.
Also, the other question, maybe I'm getting ahead, but is this? This reminds me of a little bit of compressed sensing. Can you, for example, divide your segment into? Can you discretize the problem? And it's like you're trying to do. So you represent this 0-1 interval into a segment, into a vector of length n with weight 1, because you have the position of the.
Right. And then just one of it is related. It is related to compressed sensing.
And then you can do compressed sensing, right? So you're trying to find the location of the non-zero elements.
True.
And then you can do it adaptively or non-adaptively.
True. The noise here will be different than what you have in compressed sensing, right? But otherwise.
Is that where you'll be doing, or will you be comparing to this, or that's completely?
I won't be comparing to compressed sensing. I will compare it to channel coding.
Okay.
You'll see. But definitely, you can tie these problems together.
Okay, thank you.
Okay. So a few more definitions we need. So as we said that the strategy has search resolution delta and error probability epsilon, and the probability that our estimate is more than delta far from the actual location is smaller than that. Okay, and then under this we'll have two figures of merit which will interest us, which are the same figures of merit which we have in channel coding. Basically the rate and the root. So we say that a sequence of strategies achieves targeting rate R and targeting reliability epsilon of R if these inequalities hold. And so these inequalities, I wrote them for adaptive search, but if you just take M to be 1 over delta and tau to be just a constant, we get that the rate is just the normal, the usual notation we have for rate in channel coding. So maybe it's unclear now, but we'll see. I mean, it will hopefully get clear in a few slides what rates here mean.
What is M? Capital M?
This is just notation. So I just, if you set M to be the number of messages just to 1 over delta, then you get the usual definition of rate for channel coding.
So you said, I mean, it'll be clear why you call this rate later?
What? I didn't hear.
No, did you say that it'll be clear later why this is the rate?
Yeah. Why it's related to rate and yeah. It will be rated in like 2 or 3 slides. So let's focus on non-adaptive schemes for now. Okay, and last bit of notation we'll have is that if we have a Bernoulli Q or X, which is Bernoulli Q, going into a binary symmetric channel with noise Z, which is Bernoulli P, and Y will be the output of this channel, will denote the mutual information between X and Y as mutual information between Q and P. So this is just a notation just to highlight the role of Q and P in this mutual information, and we'll see why we do it in a second. Just to say that this expression, of course, is known, right? In the binary case, the mutual information is just given by this expression. So there's nothing new here. And here's the first theorem we have. And it states that for non-adaptive search strategies, the maximal targeting rate is given by this maximization problem here. And we can achieve the random coding exponent for the channel governed by this Q star. So just as an example of this, how this mutual information behaves. So note that usually this the noise, right, is independent of whatever you do. So once you maximize this expression Q over Q, you just get Q half to be optimal. But in our case, the second P here also depends on Q. Okay, so for example, if the noise function is linear, this is how this mutual information will look as a function of Q. Okay, so no more the concave, the nice concave function we know from when of the mutual information as function of the input distribution. We get this here. And I try to give intuition why we get this expression.
So, but before, what does it mean operationally? What does the maximal targeting rate mean?
So yeah, okay. So yeah, let's get intuition in the next slide, next few slides. So to get intuition why this targeting rate and everything depends on Q. So let's start with a simple, very simple problem. We have no noise. Okay, so we want to locate a target without noise using a non-adaptive scheme, right? So with adaptive scheme, we do just binary, like divide and conquer kind of search, and we know what we should do. And with the non-adaptive scheme, we'll do the following. So we'll define a code book or a binary matrix for now. First, we will fix M to be. We'll take the unit interval and cut it into small subsets. Okay, so we'll have M such subsets, and M correspond to the resolution we want. Okay? So it's 1 over 2 delta. So if we give back the center of one of these intervals, we know that the target will be no more than delta away if we give the true. So we define a binary matrix with M rows, M corresponding to the number of subsets, and N columns, where N will be the number of queries we do. Okay? And the idea, and then for now, we just distribute 0 and 1s randomly or whatever. Just fill the matrix however you want. And the query, we do the querying in the following way. In the phase 1, for example, we turn on, we look for all, let's call these small subset sensors. So we turn on all sensors which have 1 in the first column. So for example, in the first query, we don't query the first one, we do query the second one, then not the third, and then a couple of things in the middle and the last one. In the second query, we query the first, the second, not the third, and maybe a bunch of things in the middle, and so on. So this is what we do, this is how we search. And let's think what we get as output. Let's say the target is located in the second, somewhere here, right? The second interval. Let's see what we get as the output. So whenever we query the second sensor, we should get a 1, right? There's no noise. Okay? And whenever we don't, like here, we should get a 0, right? Because there's no other target in this one target. So in the end of the day, at the end of this search, we will get the second line here as is, right? Just the whole second line is the query output. Okay, so this means when we will be able to detect that the target is located in the second line, we'll be able to detect if all these rows are different, right? Meaning that the number of queries we do should be larger than log n, larger or equal, right? So this is basically non-adaptive binary search, right? We got the same kind of, and here we have the rate, right? The rate basically is the ratio between the number of intervals we have and the number of queries we're doing. Basically, how fast can we zoom in? How fast can we zoom? Can we shrink this small? So this is targeting rate. And to the log m, we're used in binary search. Right? So in this case, rate is 1. Okay.
So again, how do you get the log m, Bob? So I understand log m from a binary adaptive search, but here, how did you get it?
So here, I wanted all my rows to be different, right?
Why they have to be different?
So what I get as output is just one of the lines, right? In this example, the second line, I get it as is. So this line corresponds to a specific sensor.
So and the sensor is outputting the sum of these?
So in the search, or in this example, in the noiseless search problem, right? So the way I search is I turn on, in every stage, I turn on all sensors in specific columns which have 1, right?
Okay.
So if the target says in the second location.
And if the column has 1 in any row, then you turn it on. It doesn't matter what row.
Yeah. I turn all of them on. So all sensors with 1 in each in the kth column are used in the kth query.
Oh, okay.
Okay. So in this example, if the target is somewhere in the second interval, whenever I query it, I should see 1 at the output, right? When there's no noise. And whenever I don't, I should see 0 at the output.
And you observe the individual output of each sensor you turn on?
No, I observe just hit or miss. Remember, I observed is the target is in my query region.
Oh, okay. So you observe kind of this summation.
Yeah. So
it's like group testing, like you said.
Yeah, exactly. So what I observe, right, is X, meaning that did we hit the target with our search?
Oh, okay.
Right. Basically, if the target is in one of these sensors or not. So what we get as output is just the line which contains the target. And then in order to detect the target, what you want is so you get a line as the output, and if there's no other line with exactly the same binary string, right, you will know which line it is.
Oh, okay.
Okay, and then for all the lines to be different, you need n to be larger than log n.
Okay.
Right? So this just shows you we can do adaptive, like we can do it at the same rate as binary search, with non-adaptives. So now let's add noise to this, and for now let's add fixed noise, right? Measurement independent noise. Just this bit is fixed is flipped with some probability. Okay, so we'll still say the target is in the second location. We do exactly the same thing, and we still get the second row here in this example as output. But just now this second row goes into a binary symmetric channel which flips some of these bits, right? So the output we see is this row with some of its bits flipped, right? So
yes.
Now when will we be able to detect where the target is? We'll be able to detect the target if this matrix is a good code for this channel, right? Because what we see as output is one of just something near close to one of them. Some of the bits of it. And then again, we know the rate, right? So we will be able to target under. We will be able to locate the target. Sorry, once if the rate of this code book is not larger than the capacity of this channel. managed.
So here you want n to be bigger than log m.
Sure. Yeah. And so log m should be smaller than the capacity of the channel.
Okay.
So this is the Goontuition and the Gandirovich. They use adaptive. We show that we don't prove anything, right? It's clear from this slide that you can do get the same rate as they did with non-adaptive search. Okay, but this is measurement independent noise because P here is just fixed. In our problem, by the way, the ratio of ones and zeros in the previous examples, you want half of the column to be ones more or less and half of the column to be zeros, right? I mean, the random coding prior for this to get this code book is half, right? The optimal random coding prior. But now, once we add measurement dependent noise, right? So now, under this scheme I showed you, the size of the region basically corresponds to the number of ones I have in a column, right? Because if all the columns is ones, I query all the intervals, and if just some of them are ones, I query the total size corresponds just to the number of ones I have in a column. At least when we speak about the unit interval, otherwise things should be scaled. So now in our problem, we have this channel which we had before, only now this channel actually depends on the code book we have, on how we search. So now, once we have this dependent, it's not clear that, I mean, it's probably not true that we should query half the region, as we did before. But there should what? There was a question?
No.
No, okay. Oh, I'm hearing. Yeah. So before we queried half the region, and now it's not clear. If we query half the region, we'll get a lot of noise. The quality of the output is very poor. So there is some of what's the size of the region to get us to get the optimal rate. And this size corresponds basically to this Q here. The random code. So if I think of this code book as random, so the prior with which I get my zeros and ones here. So if probability of 1 is Q, then this Q will govern the size of the query region. And this is the reason for the random coding prior appearing in this expression. Okay, and then again we're back. So if we look at this mutual information as we had before, so we need, as I said, because the noise depends on Q. In this specific example, the binary, the linear in a linear way, you don't want to query half the region because then you get a lot of noise. You cannot get any information out of this channel. So the speed of this example is somewhere else, 0.60. But it is a little number. Okay, so basically this is just, so I mean the scheme to get this is basically let Q star be the optimizer here, the Q that achieves the maximum, and then you draw a random code book with this Q star. So just populate this matrix according to just draw independent bits with Q star. And then, as I said, activate all sensors at time n, activate all sensors which has 1. The size of a query region is just the number of sensors divided by the total number of sensors. The number of sensors with 1 in a column divided by the total.
Excuse me.
Sure.
Here you're still assuming linear dependence?
I don't assume. No, P here is anything you want.
Oh, okay. So, okay.
Just to draw, to draw this specific curve, I need something to put as P. Right? So in this specific curve, I assume the linear dependence. That can be anything.
It's like a BFC.
Okay, yeah.
For different functions, the Q star will be different. Right? If it was instead of non-decreasing, it will be non-increasing, then Q star will be half.
Yeah.
If for big region you get small noise, then you want to the optimal thing to do is half the read. Okay, and then we do maximum likelihood decoding. So if this is a good code book and we do maximum likelihood decoding, we will be able to decode the row where the target is. Okay, so this is this almost works. Only that, I mean, in the random coding analysis, we get random amount of noise, and because these bits are random. The amount of ones in a column is under random coding is a random number. But because we have an exponential number of rows here, the probability that we get if we draw the bits with Q star, the probability that we get number of ones which is much more than Q star, or not much more, anything for plus epsilon, vanishes double exponentially fast with epsilon, with n times epsilon. Okay, so the fact that the amount of noise is random is not a real issue here, because I mean the probability that you get too much noise vanishes double exponentially fast. So in the analysis, we condition everything on this event here, on the event that the amount of noise is not larger than Q star plus epsilon. Okay? And in fact, we can assume that it's exactly this amount of noise, because if there is a column with less ones, we can always, we see the output, we can always artificially add noise to get to this level. Okay, so it's safe to assume that we have a constant noise level of P of Q star plus this epsilon. And then we basically follow Gallagher's analysis to get to the random coding error exponent. And this is almost true, because once you start, if you take IID events and you start to condition on all kinds of things, you lose. So if you throw 100 coins independently, and then you ask what's the number, you ask questions, conditioning that you got 15 heads, then these events are not independent anymore. So it's almost true that we follow Gallagher's analysis. We just need to get rid of the this conditioning we have to have. I mean, and this is possible because this event vanishes double exponentially fast. When conditioning on an event which which happens with probability going to 1 so fast, I mean, in that analysis we can throw away basically the dependence we're introducing.
So what is the result that you're trying to prove here?
So using this, we basically show that the maximal rate you get is this. And as a result, we also get that you can achieve, because we follow Gallagher's technique, you also get that you can achieve the random coding exponent for the binary channel governed by this process.
And that's a converse also, right?
This is a direct. I mean, everything here depends on this specific scheme.
Yeah, but the result does it include a converse also, or just?
Yeah, sure. Everything I say will have a direct and a converse.
Okay.
So I didn't speak about the converse, and I will just briefly speak about the converse. I will just say that, I mean, I said that the target can be anywhere. I mean, there's no distribution on the target, and then I went and showed you some random, some channel coding kind of construction. Usually in channel coding, you assume that your target, that the message is uniformly distributed over the set of messages. So we can get this, so we can move from just a number to uniform targets by using like a dithering tree. So if these are the sensors we had, to get the target uniform over the sensor, you can just shift all these sensors by a random amount. So draw a number uniform between 0 and 1 and shift all the sensors, cyclically shift all the sensors by this amount. And then under this shift, the target is now uniformly distributed over the sensor. So this is just a trick to get from like an independent number. It's just a number where the target is to a uniform distribution. And then you can apply the channel coding trick. Okay, so converse. So all I said here is good for a direct, right? It's a very, very specific scheme with these columns and how you turn on and off the sensors and so forth. For a converse, we need to deal with a continuous problem. target is somewhere between 0 and 1, and can be anywhere. So the first step in the converse is to take the continuous problems and make it a discrete one. And the basic idea is the following. So in the converse, it's safe to assume uniform location. This is part. And then we look at an interval with sensors, like we had in the direct. And the idea here is that any system which gives you the target with no more than delta, which gives you can locate your target with the resolution delta and error probability epsilon, will also give you the actual sensor with probability which corresponds to the same epsilon. Okay, so if I just take the unit interval and put my sensors on and use the whatever system you give me, your system will also indicate which sensor it is. So this is a basic step of the first step of the converse, which takes this problem back into a discrete setting, right? And then we prove the converse. I mean, of course, I'm not going into the details. Then we prove the converse to this discrete setting. So even under this discrete setting, you will not be able to do better. And the converse, I mean, so I won't go over. The converse looks like a regular channel coding converse, which I will not go over all the details. And if you taught information theory or taken information theory lately, you've probably seen exactly these kind of inequalities. This is Fanon inequality and so forth. So I'm not going over the details here. The reason I'm showing this is just to say that this converse fails when we have adaptive speed. So usually when you're doing coding with feedback, or I mean, we know that feedback doesn't increase capacity in a regular channel. Okay? And to show this, the basic way to show this in the converse of the channel coding problem is using this. I mean, at least where there's no power constraint and so forth, we use this Markov chain, which says that once you have the input to the channel, the output of the channel is independent of all the paths. Right? And this is true for channels with or without feedback, for memoryless channels. But in our case, remember, X is the indicator. So this is true in our case as well, as long as we have non-adaptive scheme. With adaptive scheme, so this X is the indicator, hit or miss. But Y will depend on the actual scheme, right? Because it depends on the size of the interval. So in our case, in adaptive schemes, Y depends on the past through the scheme that is used. So with adaptive schemes, this Markov chain fails, and this converse, or this step in the converse fails. And then it happens many times that your converse fails, but you can still prove it in another way. In this case, it fails for a good reason. So we will be able to do better with adaptive schemes. Okay, so we'll see why. Okay, so here's adaptive. So let's move on to adaptive schemes. As a first phase, first attempt, let's try to get our reliability higher. Right? Let's try to use the same scheme as before, just to make our exponent larger, right? The quality of our answer be better. So the way we do it is the following. So use the previous scheme to come up with an answer, right? With a specific sensor where the target is. And now in the second phase, just ping this target again and again. So point just this specific sensor repeatedly, again and again and again. Right? And then if this is the true sensor, you should see a sequence of ones, right, up to some noise, but this noise is very small, right? Because you're pouring only one sensor. This is the smallest noise you can get. And if you're wrong, you should see a sequence of zero. Because you're pouring a sensor where the target is not. Right? So you can see a sequence of zeros. Some of them, the zeros will be flipped again with this amount of noise. So this is basically, this is basically the Yamamoto-Ito kind of scheme, right? To get the exponent with the feedback. What we gain here, actually we gain twice by using feedback here in terms of exponent. First, we do this validation. So this gives us Berdyshev exponent, or Yamamoto, using kind of Yamamoto-Ito scheme. The second thing we gain is that we do this validation for the best channel possible, right? For best channel, our system support, we have 0. So this interval is very small. Right? So this is the point where we need our noise function to be continuous around 0. Okay, so if I draw, so this, before we had, with a non-adaptive scheme, we had the blue line here for random coding, and now we get this. Okay, so this is what we get. This is like a first attempt to use feedback here, and we use it just for doing validation. But as we saw, the converse failed, so maybe we can do better. Right, so let's try.
I have a question. I have a question here. I kind of couldn't follow what the adaptive scheme is. So what is, so you take the first measurement and then what do you do next?
So first phase I do the non-adaptive scheme we saw before, right? And this scheme gives me a specific sensor as an answer, right?
Yes.
And now I'm looking at these answers, which makes me adaptive. And I query this specific sensor, which I got as answer. I query only this sensor repeatedly for a while, for say, I don't know, 5, 10, 15 times.
Just to make sure that it's really there?
Yeah, exactly, just to validate.
Okay.
So as long as I do it in a proportion of the block of n, right, I can go anywhere. So if I do it just a finite number of times, I will be somewhere. So I mean, the number of times, so take your block, divide it into a search phase, and then a validation phase.
And then what if you realize that you made a mistake? It's not there.
So if it's not there, I restart everything.
Oh.
And again, as long as this happens with small probability, if you think of the average rate, so your rate will be the rate of the non-adaptive scheme divided by 1 minus the probability of repetition. So as long as the probability...
Adaptivity is not what I thought you would be doing. And, you'll focus on one region and then maybe narrow it down, and then, but here you just...
I'm definitely not doing this. And as we'll see, it's enough. There's no, so I mean, the scheme you're suggesting, there is works on, we have work, not my work, but Tara's student is working on a scheme like this, which is very, very adaptive.
Yeah. Because, again, in compressed sensing, there's some work on this kind of adaptive. Like after each measurement, you adapt. But I don't know if there's anything to gain or.
Yeah. So I mean, usually to get like capacity with feedback, you do posterior matching, right? Which is a very adaptive scheme in this sense. But what we show here is that to get the optimal error exponent and the optimal rate, you don't need that much of adaptiveness.
But does it increase? So here's something also I wanted to ask you. So does this adaptivity increase the rate? So it does not increase capacity, but does it increase the exponent?
So far we didn't touch the rate. We just increased the exponent, right? But we can actually increase the rate.
Does it increase the exponent? I missed what you said.
Yeah. So exponent before we got the blue line, right? The random coding error exponent.
Yeah.
And now we get this.
Oh, okay.
And this is because we can get the Brunashev exponent with feedback. This is the optimal thing you can do with feedback.
But how come you can do better than Brunashev?
No, I can. So the point here is this blue line, right? Was the channel was Q star plus epsilon, right?
Yeah.
And here I plotted the same, like the Brunashev result for channel Q star plus epsilon.
Yes.
Right, but the validation I'm doing is over a specific sensor, right? I don't have Q star, like n times Q star or m times Q star sensors I'm querying. I'm querying only a specific sensor now in the validation phase.
Oh.
So this is why I get this increase, right? I mean, I'm getting twice.
But should you not include the first phase in this analysis?
So first phase gives me rate, right? I mean, first phase will put me somewhere on like the rate which will work with will. So use a capacity. Say you use a capacity achievement code for the first phase, right?
Okay.
And then this gives you a block, right? A block.
Okay.
And then you add the validation scheme. You add another block of validation, and this basically takes you anywhere in this.
So this is the number of queries or the number of times you're gonna ask the sensor in the second phase is going to be sublinear, or it's not going to affect your rate. That's what I'm trying to.
No, it will definitely affect your rate. So if it's linear, this is what takes you from capacity all the way to 0. Depends on how much validation you are doing, right? So here the rate is 0.
Okay.
Right. So basically, I mean, use your code with any rate. Take capacity achieving, right? If you don't do validation at all, or do it sublinearly, you're somewhere here, right? The exponent is very small or 0, and rate is very high. Now, if you instead of using all your block just to do coding, right, and you use it for validation, you go down in rate and up in exponent. Okay?
Okay, thanks.
Okay, so as I said, with adaptive schemes, I mean, the converse failed, and failed for a reason, because here's theorem 2. So for adaptive search strategies, the maximal targeting rate is given by this expression here, which is a maximization of mutual information of Q and P of 0. So now the second element does not depend on Q. And again, just to see, assuming we take a linear noise model, so we got before the blue line as of mutual information is a function of Q, and this was the optimal spot. Now in the maximization of this element here, because the noise does not depend on Q, we get just the normal behavior of mutual information as a function of input distribution. Okay? And then the optimal thing is half. And we can get the Bernoulli optimal or exponent for the channel P of 0, as we saw in the previous slide. So the reason, this is how we get, so this is a huge increase in capacity. And I'm basically telling you that in some sense feedback increased capacity here. Although what I showed you is a point-to-point channel throughout. Right? But this is not a regular point-to-point channel because as we saw in the drawings, this channel depends on the code book. So we're not saying anything so Shannon was right, of course. Feedback does not increase capacity in a normal channel, right? In a channel which
if the channel is memoryless, then it does not.
Yeah, of course. Everything I said memoryless. Assuming memoryless.
But here it's you have memory, but I don't.
Yeah. So here, let me first show you how we get this increase. Okay. So the basic idea is do a couple a three-phase search. Okay, so first phase, fix a resolution alpha, which is fixed, and run again this non-adaptive scheme. Okay, say let the n be the block length and do it for a sublinear time. Right. So this phase is 0 rate. But at the end of this phase, you will get an answer. You will get in which one of the large sections the target is. Okay? And now in the second phase, zooming into this, and this is where it becomes adaptive, right? So you got your answer. Zoom in into this region which contains the target. Right? And now do everything again, just where the noise is constrained to be maximal noise, right? Can be the size of alpha. That's our maximal search region. So the previous result we saw is scaled by alpha here. But alpha is arbitrary. I mean, you can do this first phase for any alpha. Choose any alpha you want, as small as you want. So this means as long as this function is continuous around 0, what you get, because alpha is arbitrary, basically you get an optimization problem of I of Q at P0. This doesn't depend, the noise does not depend on Q. Okay, and compare this to what we had before for non-adaptive. Okay, and then in the last phase, in the third phase, just do the validation in the same way we did before. So now we got a specific answer, and just do validation to get the Bernoulli exponent for channel P0. Okay, so just to sum up these, what we saw in one plot. So this is the rate reliability of this problem. Okay, so for non-adaptive, we could get the blue line here, and this was the rate, the maximal rate of the search. With adaptive, we can get the exponent we can get the Bernashev exponent for channel for the BSC with noise P0, and with adaptive scheme, we can also increase the rate. So this the difference between this point and this point is the difference in rate we got by using adaptive. And the nice thing here is that there is no need for a converse, right? Because we couldn't do better in any sense. We achieved the capacity of the best possible channel in our system, which is this point here, capacity of BSC P0, and the optimal exponent of BSC P0. So there's no need for converse. We could never do better than this. Okay, so for adapt, this is the result for adaptive. So just to wrap up this section, so we show that measurement-dependent noise, once your noise depends on the size of your quarry, this incurs a gap between adaptive and non-adaptive. If the noise was fixed, we would not see this gap. It would be the same. The rate would be the same. Also, I mean, we just saw that there's, as you asked, there's no need for a lot of adaptive, right? I mean, a two-phase scheme will get you the optimal rate. So there's no need for a posterior matching kind of scheme to get the optimal rate here. And validation, the validation achieved the optimal exponent. So basically, we got both optimal rate and optimal exponent. So just maybe a nice extension of this problem, we can also deal with moving targets. So had we know, say we know that the target is moving with constant speed. So in this case, I won't get into the details, but basically instead, so before we looked for the most likely row in our code book, when there's constant speed, we will look for the most likely trajectory in the code book, so say diagonal in the code book. So just to give it, what we get is once you don't know the speed, if you know it's constant, but you don't know the speed, you're hit by a factor of half in the rate. And just the intuition here is that if you would have like a magical way to find the location of the target at two places at two different times, you can calculate the speed, right, if it's constant. But you'll need double the quarry, so you'll get hit the rate by half. So this is just intuition how we deal with speed. Any questions until now?
No.
Okay. So let's move on to multiple targets, and this is a shorter section. So we use the same kind of idea. So just so now we have k targets, okay? And now we assume the targets are uniform independently and uniform. We're less ambitious. So we assume that the targets are uniformly placed on the unit intervals and interval independently. Okay. Sn will still denote the quarry region as before, time n. Now the output is still denoted by y, it's still x and noise. Noise is the same as before, it's measured, it depends on the size of the quarry region. Just the x now is the indicator of a hit or miss, it indicates if I hit any of the targets. Okay, so x now denotes any of the targets, so first target or the second target or the so forth until the kth target, any of them is in my quarry region. So this is like the group testing output. We get in the lab, we get one if any sample in the quarried mixture was if there is a sick person in the group we tested. So here we get if there is a target in the region we quarried. Okay, and for now let's assume we know the number of targets. So we know there are k targets on the unit. So let's just to try to get intuition as before what's happening now. So let's say I'm using the same kind of query I used before, right? I have this binary matrix, I'm querying the columns as before. What I'm seeing now is the output. So say the target is in the two targets in the second and fourth sensors, corresponding to the second and fourth rows in the code. So now what I'm getting is output. Say no noise again. What I'm getting is output. Is I'm getting one at the output whenever I'm pouring any one of these two. Whenever there's one here, we see one at the output. here both of them, I point both of them, I will see one, and here I point just the second target, and I will still see one. So what I'm getting in the output is the OR of these lines which correspond to the target. So now the decoder will have to, it will see an OR of 2 rows, and it will have to figure out which 2 rows took place in the OEC in order to detect the target. And again, this is the basic problem of the noise, this noises problem, and the design of this code book. I mean, there are many papers on loop testing doing exactly. But we have noise. So here's basically our system. And the way we handle this problem, as we think of it, is a map, the multiple access channel. Okay, so we have two users. We have these 2 lines, right, going into an OR, and then we add noise, which is measurement dependent. So think of these 2 lines. Think of 2 users having exactly the same code book, each sending a specific line here. Right, so this is a multiple access channel with 2 users having the same code book, each sending a line, and then what I'm getting in the output is just the output of an OR map, or binary map with noise. And this, viewing this is the map problem. As before, we had a point-to-point problem. Now it's a multiple access channel problem. And again, the messages now are just where the target is, corresponding to which row each user sent. Unlike the MAC problem, I don't care, but the decoder doesn't label the target. Right? There's no, in a MAC you care if user 1 sent message 5 and user 2 sent message 7, right? And it's different than if user 1 sent message 7, user 2 will send message 5. So in a MAC you want to label which user sent what. In our problem it doesn't matter. So there's no labeling of the target, but there's no, I mean, asymptotically there's no information in this labeling anyway. Right? You need just 1 bit to label the 2, which sends, say, the smaller number of messages. So there's very little information in this, so we don't lose anything in this sense. So I mean, the main difference between MAC and our problem, is, our view of the problem, is that all users have the same code. But it turns out that in a MAC, this doesn't, as long as you use random coding, this doesn't really, this constraint doesn't reduce the possible rate, or it doesn't reduce the rate region. Okay, and the capacity of, what? Okay, the capacity of this of a binary OR MAC is just a triangle, with or without feedback. So in this case, in this kind of setting, feedback does not increase capacity. I mean, in normal without this line. So to your question, initial question, Salim, if there was a Gaussian channel here, then feedback might increase capacity even without the measurement-dependent noise.
Okay.
In this case, I mean, as long as it's binary, feedback does not increase capacity when the noise is independent of the measurement. So let's see what we already know for MAC and try to harness it. And this is where we, so first let's assume a fixed noise model. So our bits are flipped, the output of X, the OR of the indicator which tells us if we hit any of the targets, might be flipped with some fixed probability. Okay, so this is just the vanilla, the usual OR binary map. And for this, once we take this MAC problem and with k-symmetric users all having the same code book or without, and we look at the sum rate. The sum rate in this problem is given by this expression here, which is just the mutual information between half and t. So if you want the capacity of a point-to-point channel divided by the number of users. Okay. Okay. So this is known. This is just the result we take from MAC and this is in fact the rate. There was this work by Atiyah and Saligrama I mentioned. So this is the rate they get using a very different kind of tool set, and they don't see this problem as a MAC. and they work much harder to get to this. I mean, they have just measurement independent noise. So this is their model in some sense, although they're not saying it, but this is the rate they get.
But also in their model, the noise increase with the group size?
No, no. In their model, no. The noise does not increase with the group size. So
But in your model, that's what you assume, right?
yeah. This is just known results, right? I mean, in my case, I mean, in my case, you just pick your function of how the noise behaves, right? So if you pick this as a constant function, you're back here.
Okay.
Okay. Okay. So in our problem, our problem, right? We have this line here which governs the noise, right? I mean, the code book governs the noise in some sense, size of the region. So here's theorem 3. So in multiple targets, I start with adaptive scheme. Okay, so it's easier. So theorem 3 for adaptive strategies say the following. So for adaptive search in K targets, we say that the maximal targeting rate is given by this expression here, which is basically the capacity of the point-to-point channel with P0 divided by K. So comparing this to the one target scenario, the rate goes down as 1 over K. If K equals 1, we're back to the single target setting. And otherwise, as you increase the number of targets, the rate goes to 0 as 1 over K. The way to get this is the same idea we had with adaptive search before. So first phase, just try to separate the target. Okay, so do a first phase of a coarse search to separate the targets, and then once you separated the targets, zoom in separately, one after the other, into each region. Okay, and this is basically why you get the one target rate divided by K. So this seems very suboptimal thing to do, but we have a converse. So this is basically the best we can do this way. And again, there's no need for converse, because even if we had, I mean, had we started with this noise, we couldn't do better. So this is the best, as we saw for the map. This is the best we can do for this map. So in terms of, in this case, we don't care about exponents, it's just rate. We couldn't do better, so there's no need for converse. And the nice thing about adaptive strategies here that they are universal in the number of targets. So if we didn't know the number of targets K, we just had a bound, we would get just the rate which is adapted to the true number of targets. So this you can do with adaptive. Last thing I will say is what we can do with non-adaptive search. Try to give some intuition. Okay, so going back to this to the more simple MAC where the noise does not depend on the size of the region, we saw this. This is the rate we can get. And let's focus, for example, for a minute on the coding, random coding prior in here. So for the point-to-point problem, we wanted and fixed noise or no noise, right? We wanted the prior to be half. This is the capacity achieving prior. In this case, in the MAC, even with fixed noise, the capacity achieving prior is not half. What you want is that this xn going into the binary channel will be uniform. So this means that the proportion of ones here should be smaller than half. So Q star is chosen here. I'm assuming we know the number of targets, K. Q star is chosen so that when you take K of these, xn will be uniform. When you take the OR of K such bits, xn will be uniform. So Q star is much smaller than half. And the basic intuition why is that you don't want, once you get a column like this with a 2 1s, say, for both targets, you can separate the targets, right? You can you don't gain any more information than any of these cases. So you want, in some sense, to avoid collisions. You don't want to have many ones in a column. This is on one hand. Of course, if you take Q star to be 0, your rate will be 0. So there is this trade-off again, and Q star is somewhere which is much smaller than half. This is just for regular math. But in our case, once we had the measurement-dependent noise, so if before we had, instead of going to half, we had to back off a lot, now we don't need to go all the way to half anyway, even to be optimal. So now we still probably need to back off from the optimal MAC prior, but not by that much. So in what we get is this theorem 4 here that says that for non-adaptive schemes and K targets, the maximal targeting rate is given by this expression here. And it turns out that this expression is larger than what we got for non-adaptive schemes divided by K. Okay, so in some sense, the number of targets, the penalty for K targets is smaller than 1 over K, which we had for adaptive schemes. Only now we start much higher. I mean, we start much lower to begin with because we do have, this is not P0, it's P of Q. Okay, and it turns out that as K grows, this Q star goes to 0, and then we get, what we do get is the same rate we got for adaptive. So I mean, I'll show it in a plot in the next slide, but the gain of feedback here vanishes as the number of targets grow. And if we look at schematically, we get this. So this is the plot. This is the rates we had for adaptive search. So this is targeting rate as a function of number of targets. So we see this going down as 1 over K. And for non-adaptive, we start much lower to begin with, right? Because feedback increases capacity here. We start much lower, but we go down slower than 1 over K. So these curves meet at some point. Okay, so I mean, in this specific example with linear noise, I don't know, around 16, the curves are very close to each other already. So if you have 16 targets or more, there's no real gain in doing adaptive search. And this is true, of course, as long as you know the number of targets. If you don't know the number of targets, with non-adaptive, you should adapt to you don't know the number of targets, you just know an upper bound, say, and the number of targets. So for non-adaptive, you should adapt to the worst case. So for non-adaptive, if we don't know the number of targets, the green, the curve for non-adaptive scheme, it would just be just 1 point here, corresponding to the bound, the upper bound of the number of targets, where the blue one will still look the same. Yeah, so this is all I have to say. Just to wrap up, so we introduced this measurement-dependent noise model, which makes a lot of sense, and it actually makes a lot of sense in group testing as well. Not only for this search, because in group testing, I mean, they assume that if you take a sample from 1 million people and mix up, and you have only one germ there, in the basic model of group testing, we will assume that you will find the target, you will get the answer with the same kind of probability as if we had like only 2 people in this group, and only one of them is sick. So this model of measurement-dependent noise, with the noise dependent on the size of your sample, it makes a lot of sense in group testing as well. So we find basically for one target we got both the targeting rate and the optimal exponents. For multiple targets we didn't deal with error exponents, we just dealt with rate. We can deal with them when you read the papers. We can deal with constant velocity. For one target we dealt with as well. Again, under this measurement-dependent noise, feedback increases capacity. And this is because the channels are not the usual Shannon kind of channels where the noise is just given. I mean, the channel itself is given. Here, the channel depends on the actual way we search. And future work for current already, some of it is. So everything I told you about was, I mean, I used random coding. I mean, my complexity. So I can't really sell this to anyone, right? In terms of complexity, I have exponential complexity everywhere here. But it turns out you can use good codes. For example, in the point-to-point channel, if you use a good code for what I showed you, for example, in the fixed noise or no noise case, you just need a good code for the binary symmetric channel. So in our case, the prior is not half, so we need nonlinear codes, but still we can build good codes, say polar codes, with non-uniform input to achieve n log n kind of complexity, decoding complexity. So this is one way we go. So this we can do this also for the Mac. So we have like a good construction for group testing. This we hope for. Other extensions is to assume we assume the target is fixed or moving with constant speed. We can think of some process governing the movement. This becomes a much harder problem. So yeah, I can't say we advanced too much in this. We tried. Otherwise, as you asked, you can think of so binary model is very simplistic, right? So you can think of non-binary models. And this might be very interesting because at least in a multi-user setting, right, in a Mac setting, feedback increases capacity, even without measurement-dependent noise. So it's interesting to see if this translates here. You come up with schemes, even for measurement-independent noise, which will increase the rate. If you can somehow translate these matrices we have. Yeah, and that's mostly. Yeah. Thanks for listening.
Thank you. So I have a question about the last point you mentioned. So for constant noise and single target, feedback does not increase capacity, right?
Right.
But how come for multiple target it does?
Or again, maybe I didn't understand.
So I'm saying for single target, feedback does not increase capacity if the noise is constant, right?
Noise is constant, feedback will not increase capacity. Right.
Yeah, but how come if you have multiple target, it does increase capacity?
Because in a Mac, feedback increases the capacity, right?
Okay.
I mean, if you view this, so say Gaussian Mac, right? You know that, I mean, it is known that feedback.
So do you know that it increased or it may increase?
It may. No, I don't know. I don't. So I mean, in a Gaussian Mac, it definitely increases the capacity region, right?
Yes.
But as I tried to show, there is a correspondence between our problem and coding for Mac.
Yeah, sure.
So I mean, I'm not sure here because usually you get the gain by the users communicating with themselves somehow, right? And it's not clear if you can do this here. But anyway, I mean, you might. So it's interesting to see these more general models anyway.
Okay. Okay, thank you.
Good.
So, Shri, you want to conclude?
Uh,
So let's go.
yeah. All right. Thank you, Yoni.